you will use your calculators, the value of E is equal to 2.71828. So that is, yung E natin is equal to E raised to 1, right? Anything divided, any value that you raise to 1 is equal to itself. So let's try to find the value of E using Maclaurin Series Expansion. So the first step is always to find the derivative of the function. So the first derivative of the function in this case is equal to, if you will recall, the formula for the derivative of E, or the constant E raised to a function u, we take the derivative of that function with respect to x, that will be equal to E raised to u multiplied by the derivative of the exponent du over dx. In this case, your u is always a variable for you to be able to apply this, because if this is E raised to a constant, then that is considered as a constant, and the derivative in that case is just equal to 0. Okay, so let's continue. First derivative of E raised to x is equal to E raised to x, or the exponent u, multiplied by the derivative of that exponent, derivative of x with respect to x, but this is equal to 1. So we have your derivative of first derivative is equal to E raised to x still. And take note that if you will look for the value of the second derivative of this function, this will still remain as E raised to x, and so on and so forth up to the nth derivative. This will remain to be equal as E raised to x. So in that case, they are all the same. Now, what if you are going to look for the value of P of x? Remember that for Maclaurin series, you are equating this approximating polynomial to your original function. So if f of x is equal to E raised to x, then this will also be equal to E raised to x. But take note that they are only equal if x is equal to 0. Okay, they are only equal if x is equal to 0. So we can say, para clearer, let's evaluate first yung f natin, yung function natin. This will be f of 0 is equal to E raised to 0. F prime of 0 is equal to E raised to 0. But take note that E raised to 0, or a number, positive number that you raise it to the number 0, this will be equal to 1. Remember that this is up to the nth derivative, this is nth derivative evaluated at 0. So this is still equal to 1. So in that case, this will be equal to series to P of 0 and P prime of 0. Same with the nth derivative of P evaluated at 0. Now, we have your constants, C sub 0, C sub 1, C sub 2, up to C sub n. Remember that C sub 0 will just be equal to P of 0. That is coming from your function, or your approximating function is equal to P of x is equal to C sub 0 plus C sub 1 x plus C sub 2 of x raised to 2, and so on and so forth. Okay, so C sub 0 will just be equal to P of 0. Where did that come from? Take note that if you will evaluate this approximating function at 0, all the values, or all the values in the in the polynomial that has a factor of x will become just equal to 0. Kaya ang matitira is c sub 0. C sub 0 is equal to p of 0. C sub 1 is also p of 0 prime divided by 1 factorial, or leave it as is. Your c sub 2 is equal to the second derivative of the approximating function evaluated at 0 divided by 2 factorial. And your nth constant, or c sub n, will be equal to the nth derivative of the approximating function evaluated at 0 divided by n factorial. Okay? So this will just be equal to 1. The first derivative of p of 0 is also 1. This will become 1 over 2 factorial, and your c sub n will be equal to 1 over n factorial. Okay? So now going back to your original function, your approximating function is p of x is equal to c sub 0 plus c sub 1 times x plus c sub 2 x squared c sub 3 x raised to 3 plus this will be up to c sub n of x raised to n. Now we know the value of your constants, we can substitute it to the approximating function p of x. Your p of x here is equal to 1 plus your c sub 1 is equal to 1 multiplied by x is equal to x plus c sub 2 is 1 over 2 factorial multiplied by x squared. This will become x squared divided by 2 factorial. C sub 3 will be equal to 1 over 3 factorial multiplied by x raised to 3. This will become x raised to 3 divided by 3 factorial, x raised to 4 over 4 factorial, and so on up to x raised to n divided by n factorial. Now remember that the function that we are evaluating or expanding is equal to e raised to x. And if you want to find the value of e, what is the value of e? This is equal to e raised to 1. If the constant e is raised to 1, then by correspondence we can say that x is equal to 1. Now that we have your approximating function and we have already substituted the value of your constants, we can now evaluate the value of e raised to 1. So this will be equal to f of 1 is equal to p of 1. This will be 1 plus 1 plus 1 squared over 2 factorial plus 1 raised to 3 over 3 factorial plus 1 raised to 4 over 4 factorial, and so on and so forth. But for this case, let us just limit it to the sum of the first 4, or 5 rather. 1, 2, 3, 4, 5. The sum of the first 5 of the approximating function or the power series. So in this case, what is the value of the function e raised to 1? This will be 1 plus 1 is 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial. this will be equal to 2.708. But the value of your constant E is equal to the value of E is equal to 2.718. Now let's try to add another expression here of the polynomial for us to have a value that is nearer to the original. 1 raised to 5 and 1 raised to 6 over 6 factorial. So let's try to use this value. So this will become equal now to 2.1718. If you will notice, your answer, your approximating function, will become closer to the actual value of the function that you're evaluating if you will have more expression that will be evaluated in this approximating function. The lesser the values of the expression, or the lesser the sum of this approximating function, mas magiging inaccurate yung value ng function. So for you to be able to arrive with a more accurate answer, you add values for your function, of course using the pattern that is depicted by your function. So this now will become the first seventh sum of your approximating function power series. Okay, so that would be one example for Maclaurin series expansion.